This is a continuing video lecture series presenting an introduction to diodes from a circuit perspective. And in this lecture we are going to talk about the small signal diode model. So it's assumed that you already are familiar with the Shockley diode equation. If not, go back and watch the first video in this series. So we'll be using the Shockley equation to develop the small signal model. So looking at the Shockley diode model, here is the equation that describes the diode current versus the diode voltage. And as we had seen, for the region where the diode is actually conducting, this exponent is many orders of magnitude larger than 1, and so we are able to approximate it as Is times the exponential in the region where the diode is conducting. And that's the equation that we are going to use going forward in developing our small signal model. Let me scroll through this and get a fresh page. Actually, let me bring up where we left off in the last lecture. I presented several models that were useful in describing the diode VI terminal characteristics. Of course, the appropriateness of any one of these models is going to depend on the circuit in which the diode finds itself and the application that you're studying. So we'll look at that in the next video, where we'll work some problems. Here's a diode IV curve on a linear scale. The diode curve is actually the yellow curve, and over traced on it is several of the models that we have been looking at. The one in red is the constant slope model. That's the model where there's an ideal diode followed by a voltage, a constant voltage, followed by a series resistance. The idea of the series resistance is that we are not stuck having a constant slope or a constant vertical slope, but we can put an angle on this, and that angle can be fit to the slope of the actual diode curve around some operating point. Our small signal model is basically going to take this to the limit. It's going to zoom in and say, all right, what I really want is I want the exact slope right at that operating point. As you may recall from when we talked about the finding parameters or picking the values for a constant slope model, I said that you may not actually want to pick your model to exactly cross the or intersect the actual IV curve right at the operating point. So here's the operating point. Now this is the nominal value where the circuit is going to operate. But let's say that your circuit is going to operate over some range. Okay, if that range happens to be maybe from here all the way up to here, right? Then if I'm trying to minimize, I'm trying to minimize the error over that whole area, right? So the error would be at any point would be just the distance between these, right? Vertical distance. It may behoove me to not actually pick my line, my model line, to actually intersect with the operating point, because if I do that, perhaps let me redo this. Perhaps if I do that, I will have too much error at one extreme, right? My error up here is going to be larger. Even though it's 0 right here, it'll be too large at the extremes. Okay, so that's one of the things that we contend with when we did the constant slope model. The idea was that you would be trying to fit this model over some range of currents. For the small signal model, we're going to ignore that. We're going to say, hey, we're going to operate in very close proximity to this operating point. So we actually want to pick our model to intersect at the operating point. All right, and what's nice about that, let me go to a new page now. small signal diode model. Okay. So what's nice about this model is that there's no guessing in it. We're going to actually use the diode equations to derive our model. Okay, so we have voltage and we have current. This is going to be IQ and VQ, and here's our operating point. And what we'll do is I'll just zoom in here for a moment and assume we have a straight line that's at IQ, intersects this point, IQ, VQ, and there's a slope. Okay, the slope to this line is DID, right? The current through the diode with respect to with respect to the diode voltage. All right. So our Shockley equation says that ID is approximately IS e to the VD over N VT. So we need to take the derivative in terms of with respect to VD. So that's going to simply give us DID with respect to DVD here. Okay, and that will give us 1 over NVT, right, the derivative of VD over NVT, times IS e to the VD over NVT. And we note that VD is going to be equal to VQ, right? It's evaluated at the operating point. So what is this right here then? The current, this is the current that corresponds to the voltage VQ. Well, that's just IQ. All right. So we have DID, DVD, and I should have put here evaluated at ID equal to IQ. Okay. Or we could say VD at VD equal to VQ. Okay, is going to be equal to IQ over N VT. Okay, and the units are going to be mhos, right? So if this is our diode, and we have some incremental current, I'm going to put a little squiggly over it, okay? Meaning this is, let's say this. Let's say we have ID equal to IQ plus some small incremental amount of current. The voltage across here, VD, is going to be VQ plus some small incremental voltage across there. All right. The relationship between this small ID and this small VD is that ID, little ID, is going to be equal to DID with derivative of ID with respect to VD evaluated at IQ, or we can just say at Q, right, the operating point Q, that's that data point, times little VD, right, which is equal to IQ over NVT times little VD. Right? And because this has units, that this slope has units of mhos, let's define the inverse of that. Let's define little rd as equal to NVT over IQ. And then what we have is we can write that little VD is going to be equal to little RD times little ID. Okay? Such that if we have our diode here, and we look at the voltage VD and ID, and ID is this IQ plus little ID. Then VD here is going to be equal to big VQ plus RD times ID, little ID. Okay, so we can actually rewrite this, we can redraw this as follows. We can put a little resistance RD here, okay, and we can put VQ here, okay, as our operating point voltage, and our current ID, which is equal to our big IQ plus little ID, goes here. And what we really want across here then is VQ plus RD, little RD times little ID. Okay, and in order for that voltage to actually appear, what we want is RD times little ID across the resistance term. Right, but we have more than the little ID current flowing. We have big IQ. So what we'll do is we'll put in this current right here, IQ, big IQ. Okay, and we can redraw this as a Thevenin equivalent. What is the open circuit voltage on here? The open circuit voltage is VQ minus or plus the voltage across the little RD, and that voltage is minus IQRD. So we have VQ minus little RD times IQ. Okay, and then our Thevenin resistance is just RD. Right, this is our, what this really is right here is the constant slope. Okay, this is the constant slope model, diode model. Okay, fitted, call it fitted at IQ, VQ. Alright, so we actually, when I say fitted, it means intersects IV of the diode at the Q point, and slope and tangential, we'll just say, and tangential at Q. Okay? So this model here is actually useful for both DC values and small signal. Okay, so for instance, if we were to put this now into a circuit where I said, put in a resistance and we connect this up, if it turns out that, say this is Vs, and let's say this voltage is Vs minus VQ, and we have Rs here, then IQ, the current flowing, which would be defined as IQ because this is just a static operating point, would be Vs minus VQ over Rs, and of course the voltage across here then is going to be actually RD times IQ, right, plus VQ minus RD times IQ. So these cross out, and you end up with, in fact, just VQ, which is the voltage that we assumed it would be when we claimed that the voltage across the resistor would be Vs minus VQ. So this model works for the DC case, but it also works for the AC case. If we were to go back and say now Vs goes up by 1% or something, how much does the current go up? We could use this model to predict how it would increase. But when we do that, we typically don't include the operating point, the DC value. There's no need to do that. So what you do instead is you simply strip off everything except for the where you strip off all the independent voltage sources. Okay, so in our diode model, let me actually start over again here. In our diode model, we would just have RD. Okay, this here, where RD is equal to NVT over IQ, this is the small signal diode model. Okay, so if we had, for instance, this circuit here, and we asked the question, okay, if Vs is perturbed by, so it's some big Vs, and then it's going to be plus or minus some little Vs. Alright, so maybe this is 10 volts, and then this is going to be going up and down by 50 millivolts. So if Vs equals this, you know, what is Vd? Okay, well, assuming that you've found already the VQ, the operating point, then you would say Vd is going to be equal to VQ, okay, plus or minus, and then this is what we need to fill in. The way that you solve that is very simple. You take the original circuit, which would be, in this case, it has an RS, and instead of putting the diode in, you put just the small signal model, which is just this diode, or just this resistance. And then the voltage across that is just the little small signal. It's not the large signal, not the DC. It's not the VQ. We're not trying to capture that here. This is just what adds to VQ. We already have VQ here. We want to know what goes into here. Okay? So, and the voltage that we apply over here is going to just be the small signal Vs. So we would say little Vd is going to simply be Rd over Rd plus big Rs, right? Voltage division times RVS, little Vs, which is the plus or minus 50 millivolts. So suppose that Rs was equal to 500 ohms and Rd was found to be equal to 20 ohms, right? Then we would have, what would we have? We'd have 20 over 20 plus 500, or 520 times 50 millivolts, right, which would be 1/26th, approximately, okay, 50 over 26 millivolts, which would be approximately 2 plus or minus 2 millivolts. Okay, so when your power supply, Vs, is modulated, if you will, plus or minus 50 millivolts, the voltage across the diode actually changes plus or minus 2 millivolts. And what we're physically doing is, think of this curve, we are actually, what really is happening, okay, so if you are familiar with the load line, let me draw the load line for this circuit right down here, okay, for this guy. Load line. He has a slope of minus RS. Sorry, RS. Yes, minus RS. And what is happening is that, now this is current versus voltage, but and you might have seen load lines being plotted on a voltage versus current, but it works both ways. If this right here is Vs, capital Vs, okay, capital Vs, if Vs gets perturbed, how much does it get perturbed by? It gets perturbed by 50 millivolts, okay, and it would also go this way. So we could have another, and I'm exaggerating this here, making it bigger than it really is, okay. So when Vs is perturbed either way, what happens is this operating point moves up and moves down. It moves back and forth in this region here. It goes up and it goes down. And if it's a small enough region, then the actual slope of the diode curve has not really changed from what it was right at the operating point here. So you can assume, or we assume, that that slope is constant. And if the slope is constant, then who needs the nonlinear equation? Just find that slope from the nonlinear equation, replace the diode with the resistance that corresponds to that slope, and do your analysis on that. And that's precisely what is being done here. Furthermore, when we use just the small signal, what we're really doing is, here I can redraw this here if we've got our diode curve. Alright, and let's say we're operating right here at an operating point. So V, this would be IQ and VQ. What we do is we actually, it's like we use another set of coordinates. We set IQ and VQ, or we move the axes, if you will. Maybe that's a better way to do it. We look at the axes and we say this is now little VD, little V diode, and this is little I diode. Okay, and within this range, I've got a constant slope, and my slope is 1 over RD, and that's the circuit that I'm solving. Then I'll take that little small signal response, and I will add it back onto the operating point, remembering that after all, this little linear excursion here, or perturbation, is actually riding on top of a larger operating point that is itself determined by solving ultimately the nonlinear diode equation. Okay, so there's an introduction to small signal modeling of the diode. In the end, the results that you need are, this is the model, it's a resistor. The value of the resistance is simply the operating current and N times Vt. N is a parameter of the diode. You're typically given that. So it's the ideality or emissivity constant, right? And Vt is the thermal voltage, which we've seen is K, Boltzmann's constant, times the temperature of the diode divided by Q, and it's approximately 25 millivolts at 25 degrees C.